Hello, everyone. I am Yasin Gassi, PhD student in Lyon University, and today I'm going to present our latest work entitled Subjectivity-Aware Conversational Search Services. So, what's a conversational search service? In short, it's a special kind of chatbot, a task-oriented dialogue system where the task is to search for an entity over the internet. So you can search for a restaurant, a book, a flight, or even for people, for example, a dentist or a physician. And to do that, the user converses with the chatbot and submits a natural language utterance. The chatbot then reads the utterance, understands it, and recognizes the intention of the user, and then submits a corresponding API query to the underlying APIs and waits for their response before the chatbot sends back these responses to the user in the form of natural language, formatted as natural language. So this easiness of communication between chatbots and users has made users extremely comfortable when using these chatbots and has in fact skyrocketed their expectations. So now the users are no longer only interested in crude, factual, objective information, but they are seeking for subjective experiences. And unfortunately, the current version of conversational search services only handle objective information. So in this example, suppose the user is looking for a restaurant in Lyon which has a romantic ambiance and open till midnight. Here we can see that we have two objective attributes, which are the location and the time. And the current chatbots do know how to recognize these, but they fail to recognize the subjective information in this utterance, which is the romantic ambiance. One reason for that is that the objective attributes are often hard-coded and predefined beforehand. However, a user may express whatever he wants in terms of subjective preferences, and so it is not clear which attributes, which subjective attributes to include in the system, and some of them may be related, while some of them may be contradictory even. Also, subjective information is really hard to define because I can consider this restaurant as being romantic, but maybe some of you may consider it otherwise. So it's really hard to define. Subjective information has no definite truth value. Also, subjectivity is not generally structured. So oftentimes it lives in online reviews in the form of free text. So there is a need to extract it automatically. And given that we're dealing with chatbots, users expect real-time answers, so we cannot afford large processing times. In our work, we added stacks, which augments chatbots with subjectivity awareness. So we let the chatbot do its work. We let it function as it normally would until step 3. Now, in step 3, we have a set of responses from the APIs filtered with the objective criteria. And then what we do is that Sachs takes this set of results and filters and applies subjective filters that Sachs extracts from the user utterance, such that the final results that the chatbots send to the users are filtered both objectively and subjectively. So in this presentation, we have 3 contributions. So first, we'll show the abstraction that we proposed to reason about subjectivity in general. We also show the pipeline of our system to handle subjectivity. And finally, we show how we extract subjective information. To capture the broadest possible range of subjective information, we propose the following abstraction. We model each subjective information with a subjective tag, which is the concatenation of an aspect term with an opinion term. The aspect term is the feature or the characteristic that we want to be described, and the opinion term is the description itself. For example, in delicious food, food is the aspect and delicious is the opinion. We can use the same formulation to express, to model most of the subjective information we can think of, such as romantic ambiance, good atmosphere, helpful staff, comfortable lighting, and so on and so forth. So what do we do with these? What do we do with subjective information? The fundamental idea behind SACS is the use of an inverted index data structure. So here we have stored the subjective tags in the index, and each subjective tag points to a set of entities. So in this example, E1, E5, and E9 are restaurant identifiers. We can say, given this illustration, that both E1, E5, and E9 are described in their reviews as serving good food. In the same spirit, E1 and E3 are described as having great atmosphere. So when we have a new user which submits a new utterance, SACS extracts the subjective tags from the utterance automatically and then compares the extracted tag with all the tags present in the index with a similarity score. And whenever there is a match between the extracted tag and the index tag, we output the corresponding entities. And here, when I say a match, I mean that similarity score exceeds a predefined threshold. However, there is a special case when the extracted tag is not similar to any of the tags present in the index. In this case, what SACS does is that it adds the newly extracted tag to the index, and in the next indexing round, which is done offline because it takes a huge amount of time, we will extract subjective tags from the reviews and compares them to the new tag. And if there is a match, we add the entities to the index. And this mechanism allows SACS to be adaptive to new user needs because, for example, if in the first round SACS did not recognize romantic ambiance, in the following interaction, SACS will know about it. So this mechanism makes SACS adaptive. In the remaining of this presentation, we're going to focus on automatic extraction. So in this work, we define extraction as a two-step process. First, we tag each word in the input sentence as being an aspect, an opinion, or neither aspect nor opinion, and then we pair the aspects and the opinions between them. In the following example, we have in the first stage, in the tagging stage, we have tagged each word as being aspect, such as food and service, opinion, such as really good or a bit slow, and neither, such as all the other words. And then after having extracted our aspects and opinions from the input sentence, we pair them together. So in this case, we pair food with really good to construct the subjective tag really good food. And we pair service with a bit slow to construct the tag a bit slow service. Unfortunately, due to time constraints, we're not going to present our pairing mechanism in this presentation. But for those interested, please do check the paper. So here's our target model. First, we have the words in our sentence from W1 to Wn. We feed them to BERT to have their word embeddings, E1 through En. Then we use a bidirectional LSTM layer for classification. And finally, a conditional random field layer to encode dependencies between the labels. For example, an aspect in a given sentence, we cannot have an aspect without an opinion, and vice versa. We cannot have an opinion without an aspect. And there are a few more dependencies and constraints like these that the conditional random field model allows us to encode. As you can see, our model is huge, especially because of BERT. However, our training dataset is small, and this is a popular recipe for overfitting. If you're not familiar with the concept, overfitting is when your model fits the training data very well, but fails to generalize to new unseen data. And given that we're dealing with natural language, it's almost guaranteed that we will at some point encounter unseen data. Worse yet, given that natural language is very expressive, we can almost always express the same meaning in many different ways. For example, given the input sentence, I can change one word for its synonym. I can add a comma, replace a comma, and this changes the embedding layer completely because BERT is contextual. And this phenomenon adds what is called noise to the input, to the embedding layer, and our model, unfortunately, has not been trained to recognize this noise. To overcome this problem, we train our model in an adversarial fashion. The intuition behind adversarial training is that we deliberately add noise during training. So here in this illustration, the FGSM is our adversarial component. So it takes the loss and tries to maximize it by generating the worst case perturbation. Of course, these perturbations are bounded within an infinity ball, and then they are added to the embedding to generate the adversarial embedding. And during training, we use the adversarial embedding in addition to the original embedding to train the overall model, such that the model becomes robust against noise. Here, we can see that our adversarial method outperforms state-of-the-art in various datasets, but we have to be careful because large perturbations make the accuracy drop. And here we evaluate SACs as a whole against two other baselines. The first one is based on information retrieval, and the second one is a simulation over Yelp platform. And we can see that SACs outperforms the other baselines. This evaluation is a bit involved and requires more intricate explanations. So if interested, please check the paper. So to conclude this presentation, we have shown a system in accommodation to chatbots that adds subjectivity awareness, and we show how to extract these subjective tags automatically from online reviews. That's it for the presentation. I thank you for your attention, and I would love to answer your questions.